Continuing on now to phases of matter, this is going to cover solids, okay? And we've covered liquids, not gases so much, but we have covered liquids before, so now we're going to go on to solids. So solids have the highest intermolecular forces, obviously, that's why they are so close together, and therefore they also have higher melting points, okay? And so most of these compounds, they will actually have very strong ionic forces, they'll have hydrogen bonding, they will have dipole-dipole forces. Again, remember, you see van der Waals forces everywhere, but you will not say that for solid compounds, okay? Although some of them essentially have only induced dipoles. So for example, when we were talking about iodine does not have any of these forces. The only thing it has is induced dipole, and it is a solid. But otherwise, except for those exceptions there where you have huge molecules or a high molecular weight, most of the forces that you will encounter for solids are going to be ionic, hydrogen bonding, and dipole-dipole. And again, the least common is going to be the London force. So here are some different kinds of solids. Okay, now liquids is just liquid. The only thing that is different about liquids is their viscosity. Okay, which one is thicker, which one is not. But solids, there are different kinds of solids. So there is a molecular solid, metallic, ionic, covalent network, all of these. Okay, so let's talk about the different properties of all of these. Molecular solids are going to be covalent molecules which have a lot of dispersion forces, hydrogen bonding, dipole-dipole forces, okay, because they are molecular. Now remember, molecular comes from the fact that everything is going to be covalent bonded, all right, which means on the right-hand side of the periodic table. And then some of the other properties we'll come back and compare, okay? So let's go on to metallic for now. Metallic is going to be, of course, within metals. So everything on the left-hand side of the periodic table, that is metallic. And when we say metallic solid, that means you're talking about the element. You're not talking about compounds, you're talking about the element. For example, as in zinc, magnesium, aluminum, sodium, just by themselves, okay? And so they have metallic bonds, which really is not a bond. What they have is all these atoms that are packed together very close to each other, and then the electrons will kind of just freely flow around, okay, in all the atoms. So they just pack together very closely. That's the bond. And then we have ionic compounds, which, as you know, ionic bond is transfer of electrons, and it's between metals and non-metals. And I mentioned to you is that ionic bond is one of the strongest bonds out there. It's between a positive and a negative. Those electrostatic forces, which is called the Coulombic attraction over here, those electrostatic forces are very, very high. Okay, and so this is another kind of a solid. And then we have a covalent network. A covalent network is considered as a network in covalent compounds, but they're more simpler compounds, okay, not like molecules. Molecules will be a little bit different. Molecules can be a combination of a variety of atoms, whereas the covalent network will be much simpler compounds or just elements, okay, for that matter. Let's look at the properties of some of these things. Okay, so for example, the molecular solids will be soft and they will have low melting point. Okay, an example that I can give you of a molecular substance is going to be like iodine, sugar. All the examples are given to you here at the bottom. Okay, and so those will have low melting point. Metallic are malleable, and they have high melting point. We know that already. It's very hard to melt any kind of a metal except for gallium, which melts in hands, but otherwise they have high melting point. Then we have ionic substances which look very crystalline, like salt. Okay, for example, any kind of salts. Okay, they would be crystalline and they have really high melting points. Again, very high intermolecular forces. Okay, the electrostatic forces, very high. The covalent networks are also very hard, okay, and that's why we don't count them as part of molecular compounds, even though these are also non-metals for most part, but we will not count them as molecular because the kind of bonding that they create, okay, gives us a very hard texture. And then they also have very high melting points, okay, so diamonds and quartz, which is silica dioxide, as you know, okay, really, really very hard, okay, over here. So that's why they're classified a little bit differently. Molecular compounds usually are going to be insulators of electricity, which means that they don't pass electricity through. Metallic compounds, oh my God, definitely. Metals will pass electricity through without any issues at all. And metals are really good conductors of electricity. Copper, zinc, all of those, okay. And remember what I just said about the metallic bond is that the atoms are just packed together and the electrons are just flowing through all of these atoms. And so when they're flowing through, they can conduct electricity very well. Okay, so that is the metallic property. Ionic compounds will not conduct electricity on their own. Okay, but if you turn them into liquid, remember, solutions are different. I'm not talking about a solution. I'm talking about a liquid. Okay, so for example, if you take sodium chloride and you melt it, okay, into liquid sodium chloride, then they will start conducting electricity because now suddenly the electrons will become available. In ionic compounds as solids, those electrons are not available because they are part of bonding. Okay, but they will become a little bit more available if they are in liquid state. Covalent networks generally will be insulators of electricity. So diamond, yeah, very good insulator of electricity. So these are the 4 different kinds of solids that you will see. It's very hard for me to ask you any question to classify any of these, but I can. Okay, I can definitely ask you about metallic and ionic compounds because you should be able to differentiate between those two at least. So be ready for that. Another type of classification of solid, the previous one was based on chemical structure. This one is based more on physical structure. Okay, so there are 2 kinds of structures for solids. One is crystalline and one is amorphous. A crystalline substance is a very ordered substance, okay, which means that the structure of it would be very ordered and it has repeating units in it, okay, which means that you can take any part of a crystalline substance and all of the parts are going to look exactly like it. Amorphous substances are not like that, okay, they are very disordered and they can exist in however they want. There is no general structure for it, okay. So a crystalline structure would look like this, where you have a general order going on of molecules and atoms connected together, and here is an amorphous substance, okay. A classic example of an amorphous substance is like sulfur and glass. And glass is really quite unique in this because we think of glass as crystalline, because when you break glass, it seems like, oh, it's a crystal, okay, but glass is actually not a crystal. It's an amorphous substance. And a good example for looking at glass as an amorphous substance is if you go to old churches or very old buildings which have stained glass in them. And those stained glass is, of course, glass, but they've been stained with color. And you will see that if they're really, really old, okay, then you will see that a lot of them will start the color will start flowing down, okay, with gravity. And that would not have happened if it was a crystalline structure. But because it's an amorphous substance, the stained glass will start looking a little bit different, okay. So the color will start getting more condensed and more richer at the bottom, and the top will not have so, because the molecules are suddenly moving according to gravity. But this happens, you will see this only over a time of hundreds of years, okay. This doesn't happen very fast. It's a very slow moving process. So the crystalline structure, let's talk a little bit about that. I will not go too much into it, but the crystalline structure is what we call a lattice, okay. In terms of chemistry, it's called a crystal lattice. Now, if you think about this, we have so many compounds that are ionic compounds out there. We also have crystal structures for molecular compounds, all right? So covalent compounds, for example, will also have a crystal structure, but that crystal structure is going to be different from ionic crystal structure. The crystal structure that I'm mentioning now is primarily for metals and also for ionic compounds, okay? You can see some kind of similarity between molecular ones also, but a lot of these will relate to ionic compounds, okay? And so a crystal lattice then is defined as a geometric arrangement of lattice points of a crystal, and in which we choose one lattice point as the same location, okay? Which means that you have to figure out your base structure, okay? Because remember, in a crystal structure, everything can be repeated. The structure is repeated over and over and over again. So which means that you have to find yourself a place of one point of location. So you can say, okay, well, this is where I am, and everything else is going to be a repeating unit, okay? And so you have to find what is called a unit cell. A unit cell is going to be the smallest unit that is then repeated over and over again, okay? And so that is what a crystal structure would look like. One of the very key things about a crystal structure is that crystals have faces and edges, okay? This is something that you will not see for molecular compounds. So faces and edges, what does that mean? Faces mean something like this, where you have a face of a cube, and then edges, of course, means something like this, where you have a very clear edge, okay, where the two faces meet. So crystals have faces and edges. You can look under a microscope and you can tell which substance is going to be an amorphous substance and which is going to be crystalline structure, just because of those faces. So here are some of the examples of crystal lattices possible. Not all crystals are alike, and that's the fun part about crystals. You will do a lot of crystal structures if you take inorganic chemistry, because inorganic chemistry is all about ionic compounds and are all the compounds that form on the periodic table. So that's where you study crystal structures a lot more. Okay, so crystal lattice, there are about 7 common structures that you find. Okay. So cubic, tetragonal, orthorhombic, monoclinic, and all of these ones. And you can look at these and see there are some slight differences in all of them. They're not all the same. The angular thing is fine, it's all 90 degrees, but they're not all the same, okay? Some of them have larger faces than the other ones. Cubic, for example, is so symmetrical, okay? The rhombohedral, okay, this is also symmetrical, but it's like a rhombus, okay? And so they're all different, okay, in different ways. And then some of their angles also start becoming different. So all of the ones on the top, they have 90-degree angle, but as you start coming down here, where you have all these rhombuses, then of course you don't have the same bond angles. Not bond angles, crystal angles. Then you can take a cubic crystal lattice and you can further divide it into more, and you thought you were done. You were not done. Okay, so one crystal structure, one of those 7 that we saw previously, those can be divided further into these 3. Okay, and this depends entirely on what kind of compound you're talking about, because remember, you can have monovalent compound, divalent compounds, trivalent compounds. So for example, Na plus, Ca2 plus, aluminum 3 plus. So when you have these 3 different kinds of valencies, you have different combinations going on with different anions. So which means that their crystal structure is going to be different. There is no doubt about that. The other thing you have to also remember in the crystal structure is the size of the cation and the anion. Cations are usually smaller and anions are usually larger. Okay, you know that already from GenChem1. So looking at all of those different factors, a crystal structure may be very different for different compounds. You can't say that just because NaCl is one way, that potassium chloride also will be the same way, because it may not be. They have different sizes. Okay, and so crystal structure is something that we really have to study, and you have to determine the crystal structure using instruments. Okay, and I'll talk about the instrument also. Anyhow, so the cubic crystal lattice, there are 3 different kinds over here. For example, this is a simple cube, okay, where all you see is an empty cube. And then there's the body-centered cube where you'll have ions on all the corners, but and then in the center of the cube, you will find an ion as well. Okay, and this will be in the center. Then there's the face-centered cube, and the face-centered cube, you will have ions on every corner, and then on each of the faces, remember there are 6 faces, 4 on the side, 1 on the top, 1 at the bottom, and in the center of each of the faces, you will find 1 ion. So again, depending on what kind of cation anion you have, you may have all of these different kinds. And this is what it would look like if you actually had the atoms. This is like a ball and wire structure. This would be a little bit more realistic structure, okay, for a unit cell, because you can see that you have, here's the body center. You can see the entire atom in the middle here, and these are, of course, quarter or maybe 1/8 of an atom, because, you know, the compound has been sliced, or the crystal structure has been sliced. So this is kind of what they would look like in reality. For the other two kinds of solids, okay, molecular and metallic solids, the molecular are going to be very close packed structure. They would be either cubic or hexagonal. Remember, in molecular structures where you have molecules made up of covalent bonding, this crystal structure will be very different for all of them. Okay, however, in general, when you look at the large size, they would be cubic or hexagonal. All right, but if you take them at a very small molecular atomic level, then they would look different. The metallic solids are going to look like this, which, the atoms are packed together, and then you have the electrons that are going to be moving around all over the surface, okay, very easily. They're very dense structures. As we know, metals have very high density. So that's kind of what the metallic solids would look like. Here are the two structures for diamond and graphite, and I really enjoy these two structures because they're allotropes, and they are the crystalline structures for the same element, carbon, but they crystallize very differently, okay, and that makes them very unique. So for example, diamond is one of the hardest elements out there, whereas graphite is one of the softest elements out there, okay. You can write with graphite, but you cannot write with diamond, so it's very different, both of them in their structures. So diamond is a tetrahedral kind of geometry, and if you look at each of the carbon here, it will be connected to four different things, okay, or four carbons. Whereas a graphite is a hexagonal structure kind of a thing. And so when it's hexagonal, then it's much smoother, and therefore you can write with it, okay? Whereas carbon tetrahedral geometry makes it very hard, very condensed, and gives it a really good crystalline look, okay? Whereas, of course, graphite, no, does not look like crystals at all. Very different structures. I would be remiss if I kind of just didn't mention to you in passing about the crystal structures of protein and DNA. They're not part of your GenChem, but I just want to introduce this thing to you because you will probably see them later on as you take organic and biochem. Protein structures are very complicated. It takes forever to find a crystal structure of a protein, but once you have that, it gives really key information about how it functions. So for example, where the key locking site is or where the active site is. So this may be an active site, I'm not sure, but anyhow, it gives an idea of what the protein looks like in a three-dimensional way, okay, and it gives you where the reaction might take place and how things are coiled, how it is shaped, how big it is, and so on and so forth. So crystal structure of protein is really a very key thing in determining how our body functions. And then of course with the DNA, now that we know all about the DNA and the human genome has been mapped, there really is nothing about DNA that is very mysterious because it's just a blueprint, okay? But initially it was thought that the DNA holds all the secret for everything. And so the structure was very important. And it was only after the X-ray crystal structure was determined of the DNA by Rosalind Franklin, then it was determined that DNA is actually a double helical structure and not a single strand. Proteins usually are single strands, which are held together by hydrogen bonding in a different way. But DNA is a complete double strand, and it's what uh, Watson and Crick were doing was they were looking at a DNA which had a molecular weight of double than what they were thinking would look like, and it was double only because it was a double helical structure. So this is one of the most popular pictures of Watson and Crick looking at the double helical structure. The only interesting thing about this one, well, not the only thing, but one of the interesting things about the DNA crystal structure is that Rosalind Franklin never got any credit for determining the structure. She did get credit, but only as a credit, whereas Watson and Crick actually ended up getting the Nobel Prize for determining the structure of DNA. Here is what a crystallography instrument would look like, X-ray crystallography. It's a very common type of way to determine the crystal structure. Not all departments or offices or labs can actually afford an X-ray machine because it's a really very expensive machine. And then determining the structure from the X-ray machine is also very hard. It's not very easy. That's why it takes a long time. to determine the structure of any compound. Even for simple covalent compounds, it will be very hard because you first have to crystallize the substance properly. Only if your crystal is very good and clear and concise and good and pure, then only you can do a crystal structure for it. So this is a very basic schematic of an X-ray crystallographic method that we can use, and I got it from this website, and you may want to go to this one in case you want to see a little bit more about crystallography. I don't do much of it, so I can only tell you so much about this. Okay, so anyhow, the X-rays will come, bombard the crystal, and then the detector, this is where the important stuff happens. Okay, this is where the diffraction pattern will come. Once the diffraction pattern is noted, then the magic happens. Okay, and once the magic happens, then you end up getting a map. And once that map is determined with the electron density, then you get the model, okay, of what it would look like, or actually the crystal structure, okay, that would come out. These three steps here, okay, that happen, these are the key steps, of course, okay, that happen, and these three steps take a long time. Translating a diffraction pattern into something readable is very important. And what X-ray does really is actually it gives you a 3D location of an atom. So you have to use those 3D locations of each atom and then try and place them somewhere so that it makes sense. Okay, like this. So anyhow, this is where the magic happens. The concepts that I want you to know from this little presentation is the different kinds of solids. I don't go too much into crystallography and the different kind of unit cells and all that, so don't worry too much about it. Just know what a unit cell is, okay? And then just some properties of amorphous and crystalline solids. Otherwise, I don't really ask too much about this, okay? The practice sheets that I will give you in class will give you an idea of what my questions are like.